reintroduce the unit circle. Here we're going to create some functions from the unit circle. Remember, a function is just a mapping. You're mapping item A to item B according to some rule. Here we're going to be mapping angles that we measure from the positive x-axis to either the x-coordinate or the y-coordinate or the ratio of y to x. If we map an angle measured from the positive x-axis, and we're going to be measuring counterclockwise, so up into quadrant 1. So if we measure that angle and we figure out what the x-coordinate on the unit circle is, we're mapping it to the x-coordinate. We're going to call that function cosine. If we measure an angle and we map it to the y-coordinate, we're going to call that mapping or function sine. So for example, at pi over 6 or 30 degrees, the x-coordinate is the square root of 3 over 2, the y-coordinate is 1/2, and so cosine of pi over 6 is square root of 3 over 2. Sine of pi over 6 is 1/2. If you realize that you could measure any angle, you could measure any fraction, you can measure any decimal, you can measure any whole number, you can measure any multiple of pi. Also, if we rotate backwards, if we rotate clockwise into quadrant 4 then quadrant 3, those angles are considered negative. So you could also plug negative angles into our functions cosine and sine. So looking at cosine, if I start at an angle of 0, notice the x-coordinate is 1. And so my cosine wave starts on the y-axis with an input of 0 and an output of 1. If I rotate around towards 90 degrees or pi over 2, notice the x-coordinates get smaller and smaller and smaller until on the y-axis x is 0. So that's this point right here. That's this point on the cosine wave. At pi over 2, cosine is 0. Now when I rotate into quadrant 2, I have negative x values. They're still the same magnitude, they're still the same values over here. I'm getting 1/2, square root of 3 over 2, 0.8, etc. But they're now negative. So I'm getting this part of the wave. As I rotate a half circle to 180 degrees or pi radians, at that point the x-coordinate is -1. So that's this point on the wave. It's the bottom, the minimum point on the wave. And then I rotate into quadrant 3. My x values are still negative. I'm swinging around to the bottom of the unit circle. At the bottom of the unit circle, the x-coordinate is 0 again. So that's this part of the wave, and then here at 3 pi over 2, the x is 0. Now I rotate into quadrant 4. I've almost completed my full circle. As I rotate towards a full circle, or 2 pi radians, I'm heading back to an x-coordinate of 1. So that's this point here. And if I just keep going around and around and around the circle, or if I go backwards around and around the circle, I'll just keep hitting those same x values. And so that's how we create this continuous wave. It goes on and on and on. Now sine is tracking the y-coordinate instead of the x-coordinate. So if I start at 0, notice y is 0. So the graph of sine starts at the origin 0, 0. And as I rotate up towards the top of the circle, the y-coordinates get higher. And at 90 degrees or pi over 2, the y-coordinate is 1. So that's this point on the sine wave. You're at a maximum point at pi over 2. If I rotate into quadrant 2, the y values are still positive. They're not negative like the x values. And I'm repeating these same values. So I'm getting this part of the wave over here. Positive values, repetition of those values. As I rotate towards a half circle, at a half circle or pi radians, y is 0. So notice on sine, y is 0 where cosine was -1. And then into quadrant 3, y is now negative, so I'm getting these same magnitudes, but they're negative. So I'm getting this part of the wave. At the bottom of the unit circle, the y coordinate is -1. So where cosine was 0 again, that's the minimum of the sine wave, -1. Then I rotate into quadrant 4, and I'm repeating these same values, so I'm getting this part of the sine wave. And as we rotate a full circle back to 2 pi, y is returning back to 0. And again, if I keep going around the circle, I'll keep hitting all those same points at the same pace, and I'll just repeat that wave over and over again. So the domain of cosine and sine are all real numbers, because an angle can be any continuous real number. It could be negative, positive, fractions, decimals. You can measure a tiny, portion. You can measure a huge wave. A huge wave would just be many rotations around the unit circle. So all real numbers is the domain of sine and cosine. I know some of the computer programs want you to write that in interval notation. So all real numbers in interval notation means -infinity to +infinity. The range is the output, and we're going up and down in this wave between -1 and +1. So that's our range, -1 to +1. The amplitude is how high the wave goes from the center, and so the highest we go is 1, the lowest we go is -1, so the amplitude is 1. The period is how long it takes to complete a cycle. So the period, or the wavelength, is 2 pi, because it took one trip around the circle to complete the wave. The frequency per 2 pi is 1. We got one wave as we went one time around the circle. And then the center of the wave is the x-axis. It's the line y equals 0. So that's kind of the vital information about sine and cosine. Tangent is defined to be the y coordinate divided by the x coordinate. So I'm taking angles and I'm mapping the angle to the ratio that you get if you take y and divide it by x. If you think about how we kept going back and forth around the circle, and cosine was sometimes 1 and sometimes 0 and sometimes -1 and sometimes 0 again, and same thing with sine, you realize that sometimes that denominator of tangent is going to be 0, and we know division by 0 is undefined. So the graph of tangent looks like this, and the graph goes up to positive and negative infinity. So the Desmos, the graphing software I used, just didn't draw those arrows. But notice these cycles are cut off by vertical asymptotes, and those vertical asymptotes occur where we would be dividing by 0. So tangent is equal to the y coordinate divided by the x coordinate. Remember, sine is the y coordinate, cosine is the x coordinate, so you also could say that tangent is sine divided by cosine. And so where cosine is 0, or where the x is 0, then tangent is going to be undefined. And so that's going to occur at odd multiples of pi over 2 if you're working in radians. So at 90 degrees, pi over 2, cosine was 0. At 270 degrees, or 3 pi over 2, 3 is an odd multiple of pi over 2. This asymptote over here would be if we started to rotate backwards at negative pi over 2. This asymptote here is at 5 pi over 2. So any odd multiple of pi over 2 is going to be a point on the unit circle, either at the top of the circle or at the bottom of the circle, and cosine would be 0, and hence tangent would be undefined. Now with tangent, you repeat the same shape after only a half circle. You get the same exact values and the same exact pattern after only a half circle. So going to the vital information, the domain is x cannot be an odd multiple of pi over 2, because you would be dividing by 0 if you try to plug in an odd multiple of pi over 2. The range is all real numbers. That graph stretches in the y direction from negative infinity to positive infinity. The wavelength is pi because we repeat after only a half circle. You get 2 cycles per 2 pi, and our center line is still 0. It's not quite a line of equilibrium like for a wave, but notice that there's some symmetry around the y-axis. I'm getting sort of the same shape but flipped around. And actually that's where the inflection point occurs. Notice I'm changing concavity at that point. So we kind of consider this inflection point the center of the tangent wave. Now these are the basic waves, but you could have waves that have shifts going on, just like you learned in algebra class with parabolas and other graphs, that you can create all kinds of shifting. And so here we have an example of a sine wave, and the equation is 8 times sine of pi over 2, and the pi over 2 is multiplying the quantity x minus 0.5, and then there's a plus 5 on the the back end. The plus 5 is adding 5 to the sine wave, and so it's shifting the sine wave up 5 spaces. That now is the line of equilibrium. So notice I have the line of equilibrium labeled at y equals 5. It's a line, so you want to label y equals 5 and not just put 5. But that's the job of what's added or subtracted to the sine. It gives you your line of equilibrium. Notice the 8 is multiplying the sine. 8 kind of controls the slope, but when we're going up and down like a wave, it actually creates the amplitude. So this wave goes 8 above that line of equilibrium and 8 below that line of equilibrium. Notice the amplitude is 8 whether it's above or below, because it's a length, it's like an amount that you've moved above or below. So we've moved 8 above to get to the maxes, we've moved 8 below to get to the minimums. Now the pi over 2 tells you the frequency per 2 pi. So whatever number in your sine or cosine wave that's multiplying the x, that is your frequency per 2 pi. So we're getting pi over 2, or about 1.57 waves in every rotation around the unit circle. If you think about that, then every 2 pi we're getting pi over 2 of a wave. The wavelength then is this ratio, 2 pi divided by the frequency, pi over 2. If you clean that up, notice that the pi's cancel out, and you get 2 times 2, which is 4. So this wave, the wavelength is 4. You can kind of picture the wavelength by finding matching points. So if it's sine, you might want to look for where you're hitting the line of equilibrium. So notice I'm hitting the line of equilibrium and the graph has a positive slope. The next time I have a point just like that is 4 spaces away. This was at a half, and this point's at 4.5. So I moved a distance of 4 to get that matching point. And talking about the half, notice inside of the sine being multiplied by the frequency of pi over 2 is x minus 0.5. That's your horizontal shift. Again, just like you learned in college algebra with shifting parabolas and other types of graphs. If you have x minus a value, that's telling you your horizontal shift. So I'm shifting positive 0.5. I'm moving in the positive direction. Why it's the positive direction, not the negative direction, is because if I put 0.5 in for x, I'm getting 0. So basically I should get the same point as if the basic sine wave had 0 plugged in. So x minus 0.5 tells me the wave got shifted to the right 0.5. So let's look at some other examples like that. Oh, and by the way, the amplitude and the line of equilibrium end up affecting your range. So our domain is still all real numbers unless this was some application where it didn't make sense to plug negative values in or something like that. But the range gets affected by the line of equilibrium and the amplitude. So my middle is 5, and I'm adding 8. So what is 8 plus 5? It's 13, so that's the maximum range. The middle is 5. 5 minus 8 is -3. And so -3 is the minimum of the range. So this wave goes back and forth between -3 and +13. Looking at another example, here we have a cosine. So we have 5 times cosine of 3 times the quantity x plus 1 and then minus 2. So the minus 2 is telling me my line of equilibrium. It's the middle of the wave. So I subtracted 2, so I shifted the function down 2. You know, again, just like with parabolas, if you put a minus 2 on the back of a parabola, it shifts it down 2. The 5 is the amplitude. So I rise 5 above that line of equilibrium, and I fall 5 below that line of equilibrium. So the 5 is multiplying the cosine, that tells you your amplitude. Then this wave has been shifted 1 to the left, and that's because we have x plus 1. So if you put minus 1 in for x, you would get 0, so you should get a similar point as to if you plug 0 into basic cosine. So the shift is to the left 1 space. And the 3 is telling me the frequency per 2 pi. I'm getting 3 waves per 2 pi. So if here's 0 and 2 pi is about here, okay, where the graph's getting cut off. So let's count waves. 1, 2, and I don't have the complete wave, but if I went all the way to 2 pi, I would have my complete third wave. So you could see I'm getting 1, 2, 3 waves as I go from 0 to 2 pi. So the period or wavelength is 2 pi divided by the frequency, just like it was in the other example. 2 pi divided by the frequency gives you your period or your wavelength. In terms of our range, our middle is -2. If I add 5 to -2, I get 3. If I subtract 5 from -2, I get -7. So my minimum points are -7, my maximum points are at 3. And again, that's a combination of the middle, the line of equilibrium, and the amplitude. Now, to be a little more realistic, you don't have to just have flat waves. A lot of phenomena in nature are measured with waves, but the waves have more complicated lines of equilibrium. This is the CO2 data from the Mauna Loa Observatory in Hawaii over the kind of recent years. And notice it's a wave, but it's waving around a slanted line. The line of equilibrium is 2.588x plus 402.25. So that's that slanted line that we see kind of going through there. I know that slanted line's wiggly because this is real data, and real data is perfectly smooth as our functions, but our functions model the data pretty well. The amplitude of those waves are 4.105. We're using a sine function because if you chose to use 2016 as 0, Then notice how the wave's starting on the line of equilibrium, just like sine, so that's why we chose to use sine. But I could have used cosine. I mean, what would have changed is there would have been a shift in here, but that's not a big deal. You could have figured out the shift. But I chose to use sine because you don't have to worry about a horizontal shift. Then you're getting a wave every year. So every year you get one wave. So the frequency per 2 pi is 2 pi, and the wavelength is 1. Okay, so the wavelength is 1 year, and the frequency per 2 pi is this number 2 pi. So mainly it was the wavelength kind of helped us figure out what that frequency was. Every year we're getting this spike and dip, so every year you're getting one wave. So the wavelength was 1 and the frequency per 2 pi was 2 pi.